floor.
Hello everyone. My name is Klevis Imeri, and my TDK project was about improving model checking portfolios efficiency through partial result transfer. First, let's talk about some introduction and background. Software verification. Software is every day nowadays, and software has bugs, so the problem you have to solve is remove these bugs from the program, and software verification is the field that does this. So software verification is identifying or demonstrating the absence of bugs. Some methods humanity has come up with code reviews, unit and integration testing, static and dynamic analysis. But the problem is that some software is very critical software. It should not fail. For example, the software in aviation industry, automotive industry, satellites, medical industry. This software should not fail. Therefore, what we do is that we precisely verify it using mathematical tools, and this field is called formal software verification, and one of the methods in formal software verification is model checking. Let's talk about model checking. Model checking is just an exhaustive state space search, but the problem is you just don't go one by one through the state space, but you have to do it cleverly. So it's a clever exhaustive state space search. Then let's look at the big picture of model checking. You get a verification test. You put it through a verifier and you get the result. The idea is that the input you have is going to be C code in our case, and the formal method is going to be a control flow automaton. The way a control flow automaton looks is that you have these locations, you have the nodes. The nodes are locations between the lines of the program, and the statements in the program are the edges, the operations. Now let's look at the specification and property. Our property will be that we don't want to reach any error state in our program, so we're checking for errors. And the next part is that we get our formal model, we got our property, and now we put it through a model checker. And what the model checker does is it runs algorithms. The algorithms are, some of them are Seeker, boundary model checker, key induction, and so on. First we're going to explain the Seeker. Seeker is counterexample guided abstraction refinement. The idea behind Seeker is that you get your control flow automaton and you search for the state space, you keep track of the state space, and you form your graph, and you found an error path, right? And then we have to look at this graph. This is called the reachability graph because you're seeing which states are you reaching in your state space. And in this reachability graph, you have to keep track of the variables in your automaton. And you can keep track of A and B, right? And let's suppose they're Boolean variables, 4 states. A and B can be in 4 states. A, B, C, 8 states. 4 variables, 16 states. So as you can see, this grows exponentially. So we cannot, the problem is too many variables, we cannot keep track of all these variables because you get a state space explosion, right? So what we do is we just keep a subset of them, only keep track of the actual useful variables, and we keep track of them. The way we keep track is we give this new definition, the precision. Precision is nothing more than tells us what variables are we keeping track, what are we keeping track. For example, we don't keep track of A and B, we only keep track of A. But if you keep track of A, these concrete states actually become abstracted. So one abstract state represents many concrete states. And for example, this A prime, and this reachability graph, because you're representing abstract states, become abstract reachability. And you can not only keep track of the explicit value of the variables, but you also keep track of ranges using predicates. A greater than 2 or A between 3 and 4, and this is called predicate abstraction. Now the way Seeker works, the problem is that if your precision is very low, you don't keep track of many variables. The problem is that it's so abstract, you lose so much information, you can prove anything about the program. So what you do is that you run abstraction, and then you run refinement. Refinement looks, okay, so this program we need to keep track of more variables, and it updates the precision to keep track of more things. And this is called the Seeker loop. And we do it until we can prove safety or the program is not unsafe. Now another algorithm is being boundary model checker and boundary model checking and key induction. The way boundary model checking works is that you get a bound k, and you check in your program every path of length smaller or equal to k. And if you find an error in those paths, then you prove that that program has an error. But the problem is, if you get an error with a path which is longer than k, then you don't check for that error, right? And the problem, you don't check for that error. So the only way you can do this is if you increase the bound, Or you come up with another algorithm, which is called k-induction. K-induction is just an extension. You first do bounded model checking, and then you do one more step, like induction, and then you try to with all this information from the previous steps, we try to prove that there are no errors in the rest of the state space. And you can represent it in mathematical forms. After we talk about algorithms, let's talk about portfolios and corporation. The problem is that none of these algorithms is the best. Some are good at something, and some else algorithms are good at something else. So what we do is that we combine them. A way to combine them is just to run them in parallel. They don't know nothing about each other. We just run them in parallel. Another way, we can just run them sequentially, one after the other. Some examples are a predicate abstraction, and whatever happens, we do k-induction, explicit state in secret, and whatever happens in predicate abstraction, you can put them together. And these are called portfolios. The next option is that why are we just running them separately? Why don't we pass partial results between them? And that's what corporation is, passing around these partial results. And it can be witnesses, or it can be automatons. For example, here you can pass them between parallel partial results, or you can pass them sequentially. Now the common statement and conclusion. The problem here is that these corporation algorithms are extremely hard to implement, are very hard and hard to implement. And the next thing is that you have to know when to stop one algorithm, extract the partial results, and put them to the next one. So you need somehow to predict when one of the algorithms will not work anymore. So just whatever results you got, put it to the next algorithm. For this, we only have offline models which are pre-trained. And what we contribute is that a simple way to do corporation to extract partial results from Seeger and inject them into the CFA. And we give a fully online time of prediction model for the algorithms. Now let's talk about how do we extract these results. First, we do extraction. We talked about the abstract reachability graph. From the abstract reachability graph, we extract the invariants. For those who don't know what invariants are, if you look at this code, after you set A to 2 and B to 2, then at that location, A is always going to be 2 and B is always going to be 2. Or after you exit the two for loops, you exit them when A is greater than or equal to 2 and B is greater than or equal to 2. So after you exit the for loops, you have the invariant that A is going to be greater than or equal to 2 and B is going to be greater than or equal to 2. Now after we extracted the location invariants, we have to inject them. The way we inject them is that we take the location invariants, we take the control flow automata, and we add one more node, and everything which was pointing at that location, we make it point at that node, and then from that node, we make it point at the location. And the edge from the partial node to the location, we put this invariant. So every time you go to that location, you also have this invariant as information. Now, the idea is that I'm explaining here very simply, but this is quite complex. And if you take a concrete example, it will take hours to decouple it. But the main idea is that you start with empty precision, you generate the abstract reachability graph, you see that you abstracted too much, it's not going to work, you update with refinement step, you update it, and you do this loop several times until in our case it got so big we said, okay, let's stop it. After this, we extracted the invariants, and after we extracted, we simplified, and after we simplified, we take the location invariant, we take the control flow automaton, and we inject them into the code. And here I tell where they injected exactly. Now let's talk about the heuristic when to stop an algorithm. The main idea about it is that every time we got higher and higher precisions, our abstract reachability graph got bigger and bigger and bigger. And the idea behind it is that the precision gets higher, the abstract reachability graph gets larger, the computations, because the states are more complex, gets more complex. So the iteration time of one Seeger gets higher and higher. And the heuristic is that this iteration time exhibits an exponential growth. So what we do is that we try to predict this exponential growth. So we get for each iteration, we get the times for each iteration, and we put the dots, and then we fit the best exponential curve we can. This can be done with recursively squared predictors very easily. And then after we get all this information, we predict the next iteration, how much it will take. And if that prediction is more than the timeout, when we stop the algorithm. And if it's not more than timeout, then we let it continue. Let's talk about evaluation of all these results. First, we're going to see, are these partial results passing them around effective? The second one is our iteration time heuristic effective also. We implemented everything in theta, and we tested using batch execute. These are the portfolios we use: K induction 900 seconds, predicate abstraction 900 seconds, then predicate abstraction 100 seconds, after that K induction, and we also had them with partial results, and we also had them with partial results and the heuristic together. Now let's talk about the effectiveness of the partial results. We had predicate abstraction with 900 seconds, and then we had K induction with 500 seconds, and we analyzed this, and we looked where do these two algorithms fail separately, where do they fail? None of them can solve it. And it was 2,980 cases where both of them failed. And the predicate abstraction with partial results could solve 13 of them. This may not look very large, but the problem is that these errors are not only errors of the algorithms themselves, they're errors in parsing, other different errors in the whole theta program. So 13 in fact don't look much when compared to all of those, but when you get which are the good, where it can actually work, it's a large number. And then another one we tried is that the portfolio without partial results and the portfolio with partial results. From this, we looked at where it timed out, and we found 1,300 and something cases, and from this, 20 of them could be solved. Now let's look at the heuristic. For heuristic, we have this matrix, and for the matrix, we're going to focus at precision and recall. We got a low, not a very high recall, the precision was very high. So what this says is that where we could have predicted the timeout, we don't predict every time, but when we predict, that's extremely precise. So the exponential curve fit is actually quite good. If you want to ask further, the jury wants to ask further, I can also explain why the recall is quite low. The next thing is that if you put them in the graph, in the contact plot, you're not going to see a big of a difference. The problem is that you saw that from 2,000 something cases, 13 of them were solved. So the difference is very low compared to the whole cases, so you won't see a big difference when you put them in the graph. Future work in summary. So we have, well, you have to test this one because you always have to do more tests, but if we can run more tests on this, it will be so much nicer, and we will have to run some different tests which are more specific, because if you look where theta fails, it's very interesting. It fails a very specific test and you don't get a lot of results. But we have to enhance the heuristics also. As you saw, I extracted all the invariants and then injected them. Why would I inject all those invariants when I can just look at the good ones, like filter out the good ones and only inject those good ones in the next algorithm? Then we have targeted cooperation. This was the targeted cooperation. The enhanced heuristic, that what I want to talk about enhanced heuristic is that the way the predictors work is that you can add more features into it. Right here we only had the iteration time heuristic and it fit an exponential curve, but we can add more features, we can track more stuff. In the future we can make because the RLS predictors can use matrices also, and you can put more features in them. Deeper algorithm integration. Okay, we took the invariants, we put them into the control flow automaton, but we can also inject them directly into the algorithm. Not into the control flow automaton, but directly into our algorithms. And inner tool cooperation, the idea is that maybe some algorithms are good at one tool, theta, and some algorithms are good at some other tool, CPHA. And the idea is that why not pass these results also between the other tools? And here is the summary. Does the jury have any specific questions?
Thank you. Would you like to reflect to your questions? The questions from the jury?
Okay, so there was only one question that was specific for me, and the question was that I didn't include cases where. Okay, let's first talk about the iteration heuristic. So. This part, let's first call about recall. The problem is, because the question was, you didn't include cases when this doesn't work, where your algorithms are not good. So the question is, and the way I'm going to answer is by looking at recall. The reason why the recall is very low is because if you look at the graph, if you look at this graph, the closer you are in the beginning, The way we predict that it's going to explode is that if your prediction, it's so out of, when we predicted the timeout happen, it's very close to the timeout prediction that we predicted. But there are cases when after, for example, the third iteration, you explode. And the prediction is like so much lower compared to the actual real value. And that means that you were going smoothly and then you exploded, right? And that's how you measure the explosion. But the problem is that in the beginning, you have so much space for that explosion. And the closer you get to the timeout prediction, the space between the timeout and the actual prediction is so much smaller, so you don't have a lot of room to understand what is really happening at that moment. And because that room is very slow, and apparently many of the test cases were the case that the explosion actually happened at the last part. And the other thing is that for the partial results, understanding whether not good or good is quite complex, because if you want to understand exactly how you pass around these partial results and where one algorithm will be good at and when the other algorithm will fail, you have to understand exactly where these algorithms are good at. And this comes with time. This comes with time, so it's very problematic to give a simple example where partial results will not be very good. And but the idea about how to construct such an example is that you have what Seeger is good at. You have what bounded model check and k-induction is good at. And what you do is that you create a program where none of them are good at it. And that's where you get a case where partial result will be even help at all.
Okay, thank you. If I remember, there was another question about a generation of the model. It is can be done in automatic way or just manual way.
Can you
There was
phrase it?
another question.
Because I know the question. So you show several times that you started with C code.
Yes.
And then you generated, or there was a model from based on
Yes,
the C
yes.
code. How automatic can this step be done?
Generating a model is quite, Zeta already has it implemented. It's quite automatic.
So when
C code to the automaton, to the control flow automaton is automatic. It's already implemented in
Okay.
Zeta. But all the tests, not all of them, but let's say 80% of them are actually can be easily translated into control flow.
Okay, thank you. Any question from? Yes.
Yeah, you mentioned that you can inject the partial results into the CFA by introducing another node, and in the future work you said you can be more direct about it. And I got curious, what do you mean by injecting it more directly?
Okay, let's. We have to go a bit back, but at this part you could see that when we did k-induction, we get these formulas, because I explained it in a simple way to understand, but actually what you do is that you create this giant formula and then you put it to the SAT solver, and the SAT solver gives you a result. And the idea is that you can take this invariance and not put it in the CFA, but put it exactly to the queries, inject them inside these big formulas, and then when you put it immediately to the SAT solver.
Okay, thank you.
Thank you very much. Yes.
Similar question. Is there other intermediate representation like CFA or why did you choose CFA?
Oh yeah, you can have many other intermediate representation. The reason I choose CFA is that Theta has support for it already, and it's so much easier to code it when the support is already there. But you can have other models, you can define other graphs and do algorithms on them. Yeah, but the main idea is that usually in the literature they use the control flow automaton already. Like the literature has come to a conclusion that okay, control flow automaton, you see it everywhere. You have idea, okay, everyone is using it.
Thank you very much.